Okay, in this next segment, we are going to start talking about identities here in a couple minutes, but what I want to do is go back to a little bit of arithmetic practice and then some parallel algebra examples. This goes clear back to pre-algebra. A lot of people have trouble with fractions. That's the reason I want to go over this with you. And you need to become comfortable with operations using fractions. And what parallels this is algebra processes. Okay? So let's do something real simple. Let's say we had, how about 1/15 minus 5/12, and let's add one more to it. Let's say 7/18. Basic arithmetic. The way you all know that you need a common denominator here, and I'm going to go through this real fast because you folks are way beyond this skill level, but I'm showing you the world's best way to add or subtract fractions from one another. You all know you need the common denominator. The way you do it, whether it's arithmetic or algebra, is you factor each denominator into their prime factors. Tear them down as far as you can go. For instance, when you think of breaking 12 down, what do you think of, Stormy, first? 4 times 3. Did anybody else think of 6 times 2? Sure. You could start anywhere. 4 times 3, 6 times 2. Wherever you start, keep going. And we'll all end up at the same place. We'll all end up with 2 times 2 times 3. So tear each denominator down to prime factors. On 15, 3 times 5. On 18, some of you think of 6 times 3. Others think of 9 times 2. However you start, keep on going. 2 times 3 times 3. Now, what is the lowest common denominator of these three fractions? The lowest common denominator. It needs 2's, it needs 3's, and it needs a 5. How many 2's does it need? The largest group of any factor you see here in the primes. You need a pair of 2's which capture that single 2 over here. You take the largest group of any factor you see in the prime factorization. The largest group of 2's you see is a pair of them. How many 3's do we need? A pair of 3's because of what you see over here. And how many 5's does it need? 1 5. Now, watch this. 15, we have to make this into the common denominator, don't we? Common denominator here. Here's what I do always, and I've been doing this stuff for years and help lots of people in the Math Resource Center. I mark it. There's 15. What do I need to turn the 15 into the common denominator? I have to multiply the 15 times what's left here, which is clearly 12. So I have to hit this with a 12 multiplier top and bottom. Top and bottom. Ready for the next one? 5/12. I see my 12 sitting right here. I need to hit it with a, no, not a 5. A 5 and a 3, I need to hit it with a 15 top and bottom as a multiplier. And then on my 18 is sitting right there. I need to hit it with a 10 multiplier. Top and bottom. So look at what we have now. We have our common denominator, which is, which way is the easiest way to figure out the value of it? Look right here. 180. Look at the easiest formulation you see and grab it. So your fractions then are going to be a common denominator now of 180 in all cases, here, here, and here. And then on top here you have 12 times 1 minus 5 times 15 is 75 plus 70. And then you end up with negative 5 right here. In other words, that's taken away from 12, leaves a 7 over 180. check my arithmetic. Okay? Is this useful to people? Because think of where we're going. We're going to be seeing algebraic expressions like this that actually have trig functions in them. And all you're going to do is no different than what you're seeing right here to clean it up. Then, what do you need to always check when you come up with a result like this? See if it reduces. And the only numbers you need to worry about in this numerator are the factors that exist in your denominator. And you can see clearly there's no 7 in here. So there's your answer in reduced form. Do we need to do an algebra one or not? What do you think? Do we need to do something like a quadratic expression here and maybe something else here and something else there? Huh? Should I go through that? Okay, I was hoping we didn't have to, but okay, let's do it. Okay. Okay, let's see. How about x squared minus 3x plus 2? I'm just going to do 2 fractions, okay? Just a pair of fractions. And let's subtract from it something like, how about 4x squared minus 8x. And let's put a numerator up here of, say, 3. And over here, let's put something like x plus 1. Back in beginning algebra. Right, factor, okay. So we have right here, I'm seeing x minus 2 times x minus 1. Over here, I see a common 4x, and I'm left with an x minus 2. So the factors are 4, right, which is made up of 2 times 2, an x by itself, an x minus 2, oh, got it here, and also an x minus 1, right? So the LCD that exists involves all of those. 4 times an x minus 1 times an x minus 2. This particular first fraction already has this much of it, so all I have to do is come up here and multiply this thing top and bottom, numerator and denominator, by a factor of 4x. What's missing here is the 4x. Similarly, over here, I now have the 4x and the x minus 2, and all I'm missing is the x minus 1 right here. There's no difference in the process than what we saw in the arithmetic example. Okay, now go up on top here and see if you can tidy things up. So we now can build our single fraction with our 4 times x minus 1 times x minus 2 common denominator, which are in factored form. I could multiply it out to create a mess, but I'm just going to leave it factored. And up top in my numerator, I see a 4x squared plus 4x, and over here, be careful of this negative here, folks. This catches you, and watch what happens when we start doing trig identities, where we have fractional expressions involving trig things. If you have a negative out here, that negative gets multiplied in here times the 3 times has to be distributed to the x minus 1. You all know how to do that, so you end up with minus 3x there, and you end up with a plus 3 on the tail end. Check my arithmetic. Then, everybody okay this far? Tidy it up a little bit. And so we end up with a 4x squared plus x plus 3 over our LCD. Are we done? Are we done? Tell me if we're done or not. What do you need to check? Is this reducible? Is that reducible? In other words, is this numerator factorable and have any of these factors that exist in our LCD, our lowest common denominator? No, it's not factorable. Okay? You believe me? Okay. Hopefully you do. Okay. You can try. How could you try to factor this? You could sit here and play a guessing game, couldn't you? Trial and error, right? With parentheses and guessing 4x and 2x and 3 and 3 and that kind of 3 and 1, right? That kind of stuff. Or you could use your quadratic formula and see what you get coming out of the quadratic formula equaling 0 there, and see if that thing cleans up into a nice rational result. Okay, enough said. So that's what we need to know in part for being able to do trig identities, verifying complicated ones. Let me do one more thing with this, and then we will do a quick introduction of trig identities before we go to the next segment. We need to be good with cleaning up complex fractions. And we've done a little bit of this earlier in the course. And so much of trigonometry from this point on is going to be solving equations and that type of thing. So that's why I'm going back into this algebra with you a little bit. So complex fractions is another area that causes people trouble. So let me build one with fractions inside a fraction. So I'm going to have a big fraction, and inside it I'm going to have some fractions that are added and subtracted. So what if I had 2/9 plus 1/6 over, how about 5/12 minus 1/3? It could be this complex, or it could be simpler, with maybe just a sum of fractions over one other fraction, something like that. The best way to clean up complex fractions, whether they're arithmetic like this, or algebraic, or trigonometric, is to find the lowest common denominator and do what with it? Sit there until I tell you? Or Thank you. Yeah, well, I'm going to find the LCD, and then what I'm going to do is I'm going to multiply the top and the bottom by that lowest common denominator. Now here's why. When you take that lowest common denominator up here and multiply it times 2/9, the 9 is going to reduce with part of the common denominator. Then you're going to multiply 1/6 times that common denominator also, and that 6 will reduce with part of the LCD, right? So you're going to get rid of those fractions in one step right up there. Similarly, down below, multiply by the LCD, the 12 will reduce into part of it, and the 3 will reduce into part of it. So watch what happens. Off on the side, I just make a note, 3 times 3, 2 times 3, 2 times 2 times 3 for 12, and then 3 is not factorable. So the LCD we're going to need involves how many 2's? A pair of 2's. How many 3's? A pair of 3's. There's your LCD, which happens to be, we're going to multiply the numerator by it, and the denominator by it. Any questions so far? Very basic, but very critical that you know how to do this efficiently. So here we go. Two ninths times the LCD. 9 goes up into this LCD and lose the 3's, right? And you're left with a 4 times this 2. So we end up with 2 times 4. Plus, the 6 goes up into the LCD. You lose that 6 by reduction, and you're left with a factor of 6 times 1, or 1 times 6. Notice the complexity is gone. The complexity is gone. Down below, same thing. 12 takes care of 3 of our factors, where my fingers are. I need another 3, don't I? 5 times the 3 minus the 1. 3 goes up into the LCD and leaves a 12 remaining, times 12. So this turns into 8 plus 6 over 15 minus 12, which is 14 over 3. 14 over 3 is non-reducible. There you go. This could be algebra or trigonometry, right, in the structure here. Yes?
Would it get us into trouble if we just wrote 36 instead of 2 times 2 times 3 times 3?
No, not at all. I usually leave it in factored form so I can see the parts, what part of that, particularly if these numbers, if that thing's more complex, like a larger number. Less likely to make a mistake. Okay? So it takes you back to ground zero, almost basic arithmetic with fractions, but then keep in mind this carries into much more advanced type of topics. How would this show up in an identity? What if I gave you tangent of theta divided by sine theta? This is sine of theta over cosine of theta divided by sine of theta. Think of that as over 1. What's the common denominator you see here of this fraction and this fraction? Cosine theta, isn't it? Factor this denominator. Doesn't factor, does it? It's cosine theta. This denominator is 1. The common denominator, the lowest common denominator, has to have a cosine theta in it, and that's it. So all you do is you multiply your numerator by cosine theta, and you multiply the denominator by cosine theta, and you get sine theta divided by what? Help me. Look, what do you see? No. Sine theta times cosine theta. A ratio times a ratio. That has to stay there. Sine theta times cosine theta. And you reduce, right? This is a multiplier, a factor in the numerator. Here's a common factor in the denominator. They reduce out, leaving 1 in the numerator. And the result, 1 over cosine theta, we usually would write as secant theta.
So in the homework, it wants to show every one of these steps. I mean,
Nope. Am I going to show every single step of this process back here on this problem? Probably not, right? I'd probably go from this problem, maybe I'd write down 9 times 4, maybe I'd write 36 over 36 here, but then I'd write this down next. So I'm not going to show all the separate little fraction reductions. Now, what would be an identity then? What would be what we'd call an identity? The tangent of theta over the sine of theta is secant theta. Isn't this a much cleaner expression to use than this mess? Okay, so this is called an identity. An identity is a true statement for all values that exist in the domain of each of these expressions. Or in, I guess what would be the proper way of saying that? In the I'm not sure how to formally say that without thinking about it a little more. But it has to exist in places where sine of theta doesn't go to 0 because we'd have trouble there, or where secant theta would be undefined. Okay? So it has to exist in the places in the domain that the each side of the identity exist. Okay? Any questions on this reduction right here? A complex fraction, once you use your identity, the tangent of an angle is the ratio of the sine of the angle over the cosine of the angle. You now have a complex fraction. And there's a simpler way to do that. That type of structure you see. What if I had 2/3 over 5? That's 2/3 with a 5 multiplier tossed into the denominator there, 2/15. Okay. The structure there would yield the same result here. This becomes sine theta over sine times cosine. But there's the step to get you there. Okay, let me show you something briefly in the book, and then we'll go into a more formal introduction to these things. And what I want to do is show you these, if I can get them to show up here on the computer screen or on the overhead well enough. You can't quite get the book to fit all of this, but I think you can get a sense of what you see here. Let me see if I can enlarge this a little more for some of the fundamentals. Is that visible, you guys? Back in the control room? Think that would show up? Okay, good. So you know these. Tangent of the angle is the sine over the cosine. Here's your cotangent and your other ones that we're familiar with. And then come down here, sine squared, sine of the angle being squared, plus the cosine squared equals 1, the Pythagorean identity and the variations on it shown right here. And then don't forget, you also have your even odd ones, which we went over previously. So you know the sine function is odd. So if you ever see the sine of a negative angle, it's going to be a lot simpler for you to write it this way. Replace sine of minus theta with the negative of sine of theta. Okay? So that's the kind of stuff we need to make sure we know before we start verifying identities. Okay, I think that'll end this segment. You guys, back in control room, thank you. And what we'll do in a couple minutes is we'll start learning how to actually verify more complicated ones.